today we are going to talk about what machine learning is, then what's TensorFlow, how you can use TensorFlow, and where you can use TensorFlow. But before we start ML and TensorFlow in the first place, one sentence I want to start with is, a wise developer is not the one who is successfully able to integrate machine learning or any ML libraries, but is the one who actually knows when he needs ML or when he doesn't need ML. Out of 10 instances, I have found 6 developers who tell me we are trying to do something with machine learning when their solution that they're trying to build never needs machine learning at all. So that is the first thing you need to identify. Do you need to get into this scope in the first place or not? Before I get on to this, I'll just give you a brief, how to distinguish what is human learning and what is machine learning. When you were a kid, okay, and when you saw things, were you able to say in the first place that what that particular thing is? Let's say when you were a kid and I showed you this thing, would you tell me this is a bottle? How many of you would? No one, correct? So what is the first thing that you do when you see certain things is, what is the shape of this thing? Okay? And when you were a kid, the first thing you did was you will try to hold this and you will try to eat it. So it's the first instinct that comes in place. Is this thing eatable or not? That is when you classify, okay, this is not something that's eatable, let's not eat it again. Or your parents would say you, this is not something that's eatable, do not eat it again. Another thing is, you try to visually relate things, eatable or non-eatable. So what is the color of it? This is pretty much transparent, but if I give you a fruit, you would say, if it's an orange, it looks like orangish. But then again, you don't know the color is orange. It has to be given to you by someone. Okay, those are your parents, can be any of your relatives. So that is how you were able to distinguish things. One, it is round in shape when it's an orange. The color is orange. And when you try to hold this, an orange, it's basically a bit rough, has a rough surface. And when you try to eat it, it's sour in taste. That is how you are able to relate to, okay, this is an orange. Okay, that is how, as humans, you learn things. That is called human learning. What is machine learning? Machine learning is when a particular solution that you have built has a set of already given solutions, and it is able to distinguish what is the perfect solution out of it, or it's able to predict, given certain values, what is the perfect value about it. So how does the workflow looks like there are two parts in machine learning if you see it. Before I touch TF, I'll try to touch a bit TensorFlow. Before I touch TF, I'll try to touch a bit ML. A is training, B is prediction. So here again, we are taking this example of an apple. Okay. The first thing when I'm trying to train my model, I do is I try to extract the features. So what are the features? The shape, the size, the color, and taste does not play a little factor over here, but when it's human learning, it plays. So once I've extracted the feature, these features are put into an ML algorithm, which is actually training my model. And to that model, I'm also putting in the label, because I can keep on feeding data of 1,000 apples, but if I don't tell that the data relates to an apple, it would never tell me whenever I'm trying to do the prediction of a particular fruit. So that part is over. My model is now trained. The second part is prediction. Now, the label here, I have already given it, but as such, when you try to do that in Apple, it doesn't exist. I have given a certain fruit to my model, and the first thing it will do is it will again start extracting features. So when you are training, no matter you are training your model or you are trying to predict, the first step is always feature extraction. So once I have extracted the feature, it will go into a classifier model. And once it goes to a classifier model, it is using the trained data to basically give you again label. This is a very, broken down overview of what happens in training as well as prediction. It should help you to relate to what's actually going inside a solution. So this is how it works. Now let us see a use case of a particular thing, which I called a fitment of a model, which we go to before we go to TensorFlow. So let us take two assumptions. One is a tea store and one is an AB&C fast food corporation. So I just went out to a different city, and after I finished all my work, I decided I want to have some very good tea in that particular city. Now, in that city, I know there are two places which can serve me tea, okay, based on the reviews that I have read online or based on the reviews that people have given to me. Now, here the first store that can serve me good tea is called a tea store, a very generic name. What it is, it's a famous pan-India dedicated store serving 101 types of tea since last 50 years. So, of course, it will be quite a good place to go. The second one is AB&C Fast Food Co. It's a 5-year-old restaurant chain which is quickly catching up and has a very huge variety of dishes on menu and serves 2 or 3 types of tea. Uh, it could be just your masala tea or the basic teas version. So the second thing I'll do is ML converts examples into knowledge. So I just did a quick search on Google, which are the tea stores near me? Okay. Now, these are the two stores that I have already showed you in assumptions. And after the search, I realize, okay, the tea store which is famous and I like is 5 minutes away. And the AB&C fast food, which serves only 3 type of tea, is like 3 minutes away. Now, I need to take a decision where I want to go, or Google will show me results like where should I be going. So how that thing is influenced, it's basically what I have selected in the past when I'm doing certain searches. So right now, it would have definitely redirected me to the tea store because no matter it's 5 minutes away, but it's able to relate to that is my option that I would like to prefer. Now, let's bring some twist in this particular thing that's happening. There's a bridge in between the tea store and where I'm standing. Now, the time has increased to 15 minutes. Okay. Now, let's say the bridge opens up whenever a ship has to pass. So I'm not sure that it is going to take 15 minutes. 15 minutes under ideal conditions. And if a ship is passing, it can take up to 45 minutes, let's say. And certainly, you don't want to spend 45 minutes just walking to a tea store and then 15 minutes over there drinking your tea. So what I will do is, I will definitely go to the AB&C Fast Food Corporation. What I'm trying to tell you is ML is like good parenting. Garbage in and garbage out. This is a bad example and that's a bad learning, how it looks like. Don't blindly trust examples. For in this case, if there's a baby who is just 1 year old and he starts to do things perfectly fine, you ask him, eat that thing, and he'll just eats it right away. You ask him to do a certain thing, then he'll just do it right away. Then it's baby distrust. So teach ML to be cautious. Let's plot the graph on these 3 things. How far will you go to the tea store? I have the scale of user happiness and the distance traveled, 1 kilometers to 10 kilometers. These are the tea stores in a particular search, in a particular area which I have did the search. So when I take a main road and I just keep on driving on the road straight and straight and straight, thinking that whenever there's a tea store that's just on the side of the road, I'll stop my car and have the tea, then it will be called too rigid or underfit because there could be an instance where I'll just keep on driving and not reach anywhere else. And instead, I'll just neglect the place which was just next to me because I wanted to drive straight. So this is something that's not working out because I'm being too cautious with my model. Second is, what I want to do is fitting our data. How many of you know this equation? Y is equal to Wx plus B. Nice. So y is the value we are trying to predict, okay, which tea store I want to go. X1, it's the input data, tea stores around me. W1 and B are the values we are trying to fit or learn from the data subscripts will be useful for problems with more dimensions. But it's not often fitting. We often use linear methods as model, but ML is more than just fitting the points we have. We need a line that generalizes well to a new, previously unseen data points from the same distribution. So what I'm trying to say over here is, when I start on my journey to find a tea store around me, this model or this equation should give me a result which shows me the nearest store with a perfect path. Okay? It shouldn't just make me drive down the road monotonously, or it shouldn't take me literally to every tea store that comes in way. But this is what the good learning should or actually look like. It's never a straight path. Instead, it's a curve, and it will go exactly through the places which is nearest to me. Like if you see, this was the nearest tea store, the first one, so it takes me there. The second nearest tea store was that one, okay, and the result is based upon traffic conditions, if the road is closed or not. This is called product excellence, or this is how fit should be. Now, how can you get started with machine learning? Step one, how many of you have used Google Cloud? The first one is you can use Google Cloud. We have a bunch of offerings like Vision API, Speech API, Natural Language API, and Translation API, and get your thing done. This is very easy to do, but you do not have much control on what type of model is being there. Second is, again, you can use Google Cloud. You can use cloud storage to store all your data sets. Then you can use BigQuery, and you can develop model and test over there. Here again, you have a bit flexibility on your model. And the last one is you can use TensorFlow on your local hardware or on your machines. So what happens here is when I'm traversing from 1 to 3, it's more modular, but more effort as well. I'll get the modularity what I'm looking for, but the effort spent will be much more higher than I'm doing in the first step, because in step A, I'm just using an API to get my stuff done. But here, I might want to write my model, or might take, let's say, inception and train it again. I'll try to show you what TensorFlow can do for you. A comparison between synthetic data as well as real-time data that we have done already, and where we are using TensorFlow inside Google, the products, and what are how TF is helping in medical science in early recognition of diseases. Okay. So what is TensorFlow? It is actually machine learning from everyone. No matter you are a student or a researcher, it's made in such a way that everyone can use it. It's fast, flexible, and production ready. It scales from research to production quickly. So if I want to actually distribute it, or if I want to break down these two words, tensor and flow, tensor is a multi-dimensional array of a graph of operations. So I want to show you how the DFG looks like, the data flow graph. So this is the graph of the same code that is written in Python. If you see that, what is not clearly visible, but I'll just tell you. I'm taking two parameters. I am inputting the data into my model. Then I'm seeing what is the loss, and then I'm trying to write a loss optimizer, and then I'm just getting the output of my results. The same thing can be denoted using a DFG. And this is how would the TensorFlow graph look like. TensorFlow supports many platforms, CPUs, GPUs, TPUs, tensor processing units. TPU is a specialized hardware built from ground up inside Google to run TensorFlow. And the results when you are running in comparison with GPU and TPU, the TPUs will give you much, much better results. Right now, TPU is not available as a hardware for general public to buy, but it's there on Google Cloud, and you can create an instance, and you can use TPU to train your models. Then again, TPUs are still not available for public usage. Startups can apply for it, or universities can apply if they are doing research on TF for a TPU cluster. And iOS, Android, and Raspberry Pi. When I'm talking about iOS and Android, you are actually not running your models on these mobile devices. Instead, only the results or the serving is done on these devices. For example, there's something called as ML on watch. If you are using Inbox, it will give you a suggestion on your watch itself to reply back to those emails. If you have used Inbox, it always gives you a suggestion with 3 or 4 suggestions, like these are the possible reply you can do, no matter you are on your phone or you are on your watch. So it's not necessarily training or running those models on your phones. It's actually done somewhere else on the server. It's only the tf.serving part is what's happening on your devices. A lot of languages are supported over here: Python, C++, Java, Go, Haskell. TensorFlow provides great tools like TensorBoard as well. So TensorBoard allows you to do a visualization of data that you have. So it allows researchers, when they are dealing with convolutional models, to see where the data is going, or from which point to which point the data is going. It makes their task much, much easier when they are doing this type of research. So if you want to try out TensorBoard, you can go to TensorFlow's website, and then just do a quick search for TensorBoard. It's available on the web, and we promise you that you won't break, no matter what you want to do with it. So you can just try it out. Ways to use TensorFlow, or how we have been using. The first one is neural machine translation. How many of you are using Google Translate? How many of you used Google Translate 3 to 4 years back? So if I want to ask you what the quality of Translate 3 to 4 years back and today, how would you rate it? Much better? So translation was always used something called as face-based translation, face-based machine translation or PBMT, where a bilingual translation technique was used. Sentence was broken down word by word, and the translation was made to it and was presented to the user. When I used it 5 to 6 years back, sometimes it just wouldn't make sense because it would be incorrect. Even though the words are literally translated what they were supposed to be, but when they put it into sentences, it was actually, if I tell to someone, the guy who was native in that language would, I'm not sure if he would understand it or not. But right now we have one more layer on top of it. It's called the neural machine translation or NMT. What does NMT does is it has significantly reduced the code base which was earlier used in face-based machine translation, like thousands of lines to few hundred thousands of lines. That's it. Okay. Now, one more thing NMT has allowed us to do is increase the accuracy or decrease the errors, in some cases still 85%. If you see the translation English to Spanish and English to French, the error rate is much, much lesser after NMT was implemented. NMT was implemented just last year. If you want to read more about NMT, you can go to Google's open source blog and just read the article. Show and tell. So here there are two images side by side. One is a blue and yellow train traveling down train tracks and a person on a beach flying a kite. So when I say a blue and yellow train traveling down train tracks, do you think this sentence literally makes sense for you? How many of you agree to this sentence, a blue and yellow train traveling down train tracks? But the point that it's close enough to tell you at least it's not a car that's traveling down train tracks, but a train. Now in the meantime, if I see the other thing, a person on a beach flying a kite, but what's a glacier doing over here? On a sunny beach. Okay. So images can be super tricky sometimes, but it's still trying to tell you, it's looking at the images. That's why we call it show and tell. That is a person on a beach who's trying to flying a kite irrespective of the glacier, and there's also a pirate ship in the background on the seas being there. Number of Google directories containing model description files are this much, like search, Gmail, Translate, Maps, Androids, and research used for hundreds of papers and projects. So you can go to TF or any of the project and you can see the model description files and find out which models they are using. It's very, very easy. You just have to use GitHub. How many of you use GitHub? How many of you make active contributions or active commits on GitHub? Interesting. And incidentally, TensorFlow is also the #1 repository in machine learning category on GitHub. This is what TensorFlow was in the starting of 2017. And this was what it looked like after we did the TensorFlow Dev Summit last year. Around 50,721 star counts on TensorFlow's repo on GitHub. Just next to it was scikit-learn. Scikit-learn was in fact the first library I started with ML some 5 to 6 years back. And then there's Caffe, CNTK, MXNet, Torch, and Theano. Again, if you are interested in TensorFlow, the TensorFlow Dev Summit is happening on March 30th. You can go to TensorFlow's website and see the live stream over there about the recent announcements as well as the talks. Now, TensorFlow, a vibrant open source community, it's rapid development, many outside contributors, around 475 plus non-Google contributors to TensorFlow 1.0 were there. 14,000 commits have happened in last 14 months, and it's increasing. Many community-created tutorials, model translation projects. That's the beauty of open source. Because the library is open source, you can just go on YouTube, and you can see a bunch of people trying to make video tutorials on how do you get started with TensorFlow, how you can implement TensorFlow in your solutions that you are building. And use in ML classes is growing, like Toronto, Berkeley, and Stanford already has TF as a particular course offered. TensorFlow version 1.0. So after 1.0, these were the 3 primary things that came into place. Fast, it has a 58x speed up on 64 GPUs for the Inception V3 model. higher level interfaces and stable API serving. So just let's talk about the speed up. So here is a side-by-side comparison of training of synthetic data. So P100 and K80 are actually the GPUs that are offered by NVIDIA. One thing you have to make sure is when you are using TF on a GPU, it has to be CUDA enabled. So make sure whenever you are planning to buy a GPU, it has CUDA in it. Okay, else you won't be able to use the power of it. So the blue line that you are seeing is actually ideal scaling. So add n number of processes and get x times speed up. So if you see that in real world conditions, it's actually not possible in most of the cases. But here with using synthetic data, we are trying to show you, like after using TF, we are able to actually get to that perfection. Now, people are mostly interested on what happens when I am doing this test on real-time data. This is it. So not much difference when I'm switching from synthetic to real-time data. Still, on P100, I'm getting a 7.2x speed up comparative to the 7.3x speed up. And on K80 from 7.5x, I'm at 7.3x speed up. Higher level interfaces, so this is what the same code is written on low level Python API, and this is what is written in higher level Python API. While this is done using 15 lines, when I'm using a high level Python API, 7 lines are used. The ambiguity increases, but it's much useful when you are writing large solutions because the lines of code that you are writing can reduce in terms of thousands of magnitude. So instead of writing 1,000 lines of code, you can just get your task done when you're using a high-level Python API in 500 lines of code itself. Stable API serving, so in case you are using a TensorFlow model or you have built a model that is using TF lesser TF 1.0 version, then we have a script for you to convert Python code to 1.0. You can just use the script and upgrade from 0.9 or 0.8, whatever you think you are running, to 1. And API compatibility, Python API backwards compatible through 1.x.y. Saved model backwards compatible. Again, you can go to tensorflow.org, this link, and basically learn more. TensorFlow case studies. Mobile deployment. So this was a translate thing I was talking about. You just point to a thing and it will tell you, it will give a literal translation in different languages. These are the products that are used. YouTube, whenever you open YouTube, you will always see the videos that you want to see. Not something that you don't want to see or not in a language that you usually don't speak or don't understand. Play, it will always try to give you suggestions based on the apps that you download or use. Second, Translate I already talked about. Cloud, you can use much more on Google Cloud when you are talking about ML. If you don't want or if you are not having enough hardware support, you can just go there and do it. Case studies in medicine. So TensorFlow has been successful in early recognition of diabetic retinopathy, DR in this case. So this is an image taken of the backside of an eye of a healthy person over here. And this is the one of a person who is having some disease, okay, or having DR already. So there are hemorrhages on the diseased person while they are not unhealthy. So it is TF allows us before this hemorrhages comes in place to actually recognize, okay, this my guy might get DR in the near future. So these are the steps you should, or the doctor decides which they can take and actually stop this from happening. What are the next steps? If you are interested in getting further into TensorFlow, these are the bunch of tutorials I've listed down. You can just go to there like tensorflow.org for tutorials and code. Intro to Deep Learning with TensorFlow, there's a Udacity class on it. Stanford CS 231N course. Udacity is machine learning nanodegree, and if you are totally new to ML, you can go to YouTube and try out or have a look at Josh Gordon's machine learning recipes on Google Developers channel.